Hello everybody. In this video recordings I'm going to be doing some of the problems associated with lecture 16 of the linear systems. So there are a whole bunch of problems that are listed at the end of the lecture. What I'm going to do today is just go through some of them and perform the actual computations and show you how you use some of the tools that you're given in chapter 16. The primary tools that you're going to be using are the set of properties of the Fourier transform, which are given at the beginning of the chapter 7, and then there's a table on page 702, which is table 7.1, that gives you a lot of pre-computed Fourier transform pairs that you're going to be using in some of these problems, and which is also going to be available for your quiz. So you can assume that this table is given on a quiz. However, as I always say, it's the more you know, more of these entries you know by heart, easier it becomes in a time crunch. So let me do some of the problems. The first problem I'm going to do is problem 722, and that one actually is not requiring us to use the table, but it says from the definition of the Fourier transform, show that the rect of t minus phi is Fourier transform with a sinc of omega over 2 e to the minus j phi omega. Okay, so this function rect of t over t0, or another notation is phi over t0, is defined as a function which is 1 for t smaller than t0 over 2 and 0 otherwise. In other words, it represents the square pulse that's centered at the origin and then has a width of whatever is downstairs. So by looking at this, this would be a pulse that is, let me just draw it, that's, you can think of this as a rect of t minus 5 divided by 1, which means that the pulse is centered at 1. It is it's centered at 5. This is 4.5, and this here is 5.5, and the height of the pulse is equal to 1. And the problem says use the direct definition of the Fourier transform to find the Fourier transform of this time domain function. So you probably know by now that f of a Fourier transform of the function x of t is given as an integral when t goes from minus infinity to plus infinity x of t e to the minus j omega t dt. Notice here I'm I'm using the omega definition of the Fourier transform. There's a dual definition where you use frequency. For this problem, what I'm trying to prove here is given as a function of omega, I'm going to use the omega here. In most books on communications and particularly in communications, we use frequency here, so it's always 2 pi f. Your book and many other books favor omega. It's all the same. You're going to be working with either one of them depending on the circumstances. So let me now evaluate this integral. So this becomes integral when t goes from minus infinity to plus infinity, rect of t minus 5 e to the minus j omega t dt. Now this rectangular pulse does not is 0 before 4.5, and it is 0 after 5.5. So I have x of omega, which is this Fourier transform, is integral when t goes from 4.5 to 5.5, and in this interval the pulse itself is equal to 1. So it is 1 e to the minus j omega t dt, which I can easily integrate. This is e to the minus j omega t over j omega, 4.5, 5.5. You should note here that I have switched the boundaries of integration because there's an extra minus that was brought downstairs. So this is now 1 over j omega, e to the minus j omega 4.5 minus e to the minus j omega 5.5, close the boundaries. And now the trick is, can I make this fit this particular form? Well, let me see what I can do first. I can take the e to the minus j omega 5 omega outside. So this becomes 1 over j omega. When I take e to the minus j 5 omega, what I'm left here is e to the j 0.5 omega minus e to the minus j 0.5 omega e to the minus j 5 omega. And then I can divide and multiply by 2. So this becomes e to the minus j omega over 2 minus e to the minus j omega over 2 over j omega over, let me just do it this way, j 2 times omega over 2. Now, it's easy to recognize that these two terms, along with this, they form sine, and this is equal to sine. Oh, and I'm forgetting the e to the minus j 5 omega. And then it's easy to see that this is sine omega over 2 over omega over 2 e to the minus j 5 omega, which is sinc of omega over 2 times e to the minus j 5 omega, which is what was asked to be proved. Proven one thing that you should keep in mind, your book defines sinc of x as sine of x divided by x. That's the definition of the sinc in your book. There's an alternative definition where sometimes it's written like this, sine pi of x, which is sine pi of x over pi x. This one is most commonly used in communication books, but in your book the sinc is just the sine x over x. Okay? So that's an easy problem. The key in all of these problems is to just be patient and then take one step at a time and make sure that you don't make silly mistakes, because there's a lot of going from one line to the next one where the mistakes can be made. Now, this is a long way of doing this problem. Let me actually do this problem how, not doing it manually, but instead using the table that you have given. So I'm going to use this section of the board. If you go to the table that is given on page 702, the item, let me see here, the item 17 says that rect of t over tau has a Fourier transform of tau sinc omega tau over 2, right? So that's the first thing that we know. Now, another thing that we know is this. This is a time shifting property of a Fourier transform. It says that if x of t has a Fourier transform x of omega, then x of t minus t t0 has a Fourier transform x of omega e to the minus j omega t0. In other words, delay in a time domain by the quantity of t0 amounts to this extra exponential factor here that represents the phase shift in a frequency domain. Now it's interesting, and we a little bit talked about it when we were talking about the Fourier series. But what this means physically is kind of intuitively clear. When you delay your signal in a time domain, the magnitude response of the signal cannot possibly shift. It cannot possibly change because it's the same sinusoidals that are building this signal and this signal. The only difference is that the sinusoidals that are building these signals are delayed in time. And what we know about a sinusoidal, if you want to delay it in time, all you need to do is do the phase shift. So all the changes that are happening when you're delaying the signal in the time domain are actually happening on the phase spectrum of the Fourier transform. Now, how do we put these two together to get the same result here? Where in our case, tau is equal to 1. That tau here is the width of the pulse, right? In the general case, this is tau. In our case, it is 1. So we have rect of t over 1 translates into 1 times sine, omega times 1 over 2, which is this sinc omega over 2. And then rectangular of t minus 5 translates into sinc omega over 2 e to the minus j 5 omega. And this is how somebody experienced with Fourier transform would do it. Because just we all know this time delay property, time shifting property, and it's easier to do it this way and less prone to mistakes. So this is problem 722. Let's look at the next one. This is a problem 731. And this problem has several problems in it, A, B, and C. I'm going to just do, let's say, one of them. And it says, apply the duality property and appropriate entries in the table to determine the Fourier transform of some of these functions here. What is the duality property? If x of t has Fourier transform x of omega, then the question is, where this is capital now, what is the Fourier transform of capital X of t? That's a duality property. In other words, if this is a lowercase, a little bit difficult to show that on a whiteboard. So if x of t has a Fourier transform x of omega, then what is the Fourier transform of x of t? The way how we can address this is we're saying, okay, x of omega is going to be, let me see, it is, maybe it's easier to do it this way. X of t is equal to 1 over 2 pi integral when t goes from minus infinity to plus infinity, x of omega, or let me just say like this, x of some u e to the plus j 2 pi, I'm going back to my communication stuff, e to the u t d u. In other words, x of t is the inverse Fourier transform of x of u. from here, if I multiply both of them, I can say with 2 pi, I can say that 2 times x of t is equal integral when t, again, not paying attention here. This is u, right? U goes from minus infinity to plus infinity, x of u, capital X of u, e to the j u t du. Now, if I substitute minus t for t, then I get 2 pi x of minus t is equal to u goes from minus infinity to plus infinity, x of u e to the minus j u t du. And so now if I do substitution here, and instead of u, I substitute that with t. Trying to figure out x of t is that, so this is 2 pi x of, and if I use a substitution t is omega, then I can say 2 pi x of minus omega is equal integral when t goes from minus infinity to plus infinity, capital X of t e to the minus j omega t dt. Now what you see here is the Fourier transform of capital X of t. So then x of t has the Fourier transform 2 pi little x of minus omega. Right? So that's the duality theorem that allows us to, calculate sometimes it's easier to do Fourier transform of time domain, sometimes it's easier to do Fourier transform of the frequency domain. But this tells us if I know the Fourier transform of the time domain, it is really easy to determine the Fourier transform of the frequency domain. All I need to do is to take this x of t and substitute minus 2 pi minus omega. So that's a formal derivation of duality. That's it. Duality. Let's look at an example here. How would one use that? So let's look at problem number B. It says delta of t plus capital T plus delta of t minus capital T has a Fourier transform 2 cosine t omega. So that's what is given. We need to show that. So it says show. And then, so I guess this would be here 2 pi x of omega, or minus omega. And, no, sorry. This would be 2 pi x of minus omega. And then this would be Fourier transform of capital X of t. So we start by signal x of t equal to 2 cosine t omega t. Omega t. And what we are wondering is what is, so this is Fourier transform of this, we know. Fourier transform of cosine is again in this table. And let me see, should be one of the first. They have it omega 0 t. Let me put it omega 0 t here. it's equal pi delta omega minus omega 0 plus delta omega plus omega 0. That's one of the Fourier transforms. So now the question is, what is so x of t? So if this is x of omega, the question is, what is the Fourier transform of delta t minus t0 plus delta of t plus t0, which is this guy, but let me also put pi here so that we have Fourier transform of x of t. And according to the duality theorem, this is going to be equal to 2 pi times the appropriate x function here, where instead of t, I put minus omega. So this becomes times 2 cosine t0, and instead of t, I put minus omega. Okay? So now I use the property of the cosine that it is even function. So this becomes 4 pi cosine t0 times omega. And I have an extra 2 somewhere. So I wonder where is this 2 coming from. Fourier transform of this guy is that. Right? So so there is a, this is from the table. This is the entry number 9. So the cosine omega 0 t has this as a Fourier transform. Therefore, I'm here just making a substitution t0 for omega 0 to be the same as upstairs. So now if I put t here instead of the argument, then this has 2 pi times this guy, where instead of t I have minus omega. So this is equal to this. And then if you eliminate pi on both sides, you get that the Fourier transform of delta t minus t0 plus delta of t plus t0 is equal to 2 cosine omega t0, which is the same as the statement we were trying to prove. Now, this theorem comes really handy in some cases. This is a little bit constructed case. I guess, chose it randomly. But you will, in case you get stuck, and it's very difficult to get the direct Fourier transform. Maybe, if you were to apply it in the opposite direction, you actually end up with a easier result. Okay. So that's problem 731. 732. It says the Fourier transform of a triangular pulse in figure 7.3-2. Okay, well, which one out of these many triangular pulses? P7. Okay, use this information, show that, all right, so let me, so it's 7.3-2. We are looking at the signal that looks like this. Let me just draw it. This is what we call lambda t over t. Right? And that's a triangular pulse. Let's see if I have actually yeah, use the same now it's in the other direction. Now, the lambda can be defined different ways, so I'm not sure which one is in your book, but let me do this. And then let's find out first the Fourier transform of this guy. The easiest way to find the Fourier transform of this one is to look at the function, look at the property of the Fourier transform that says that if x of t has a Fourier if I have any t derivative plus minus, let me just then do it. So here the Fourier transform of lambda of t over tau is going to be integral when t goes from minus infinity to plus infinity, lambda of t divided by tau e to the minus j omega t dt. Now, this function lambda here, as you can see from the graph, is an even function. Therefore, is the Fourier transform of the triangular waveform, and this is given by definition. Now, this can be written as, because triangular waveform is even function, then I can only integrate over the positive t, but I have to make sure that only even part of this exponential is taken into account. That's the most common mistake, because a lot of times you find students treating this as if it were even, but the matter of fact is it contains even part cosine omega t and then odd part, which is j sine omega t. So I can write this as integral when t goes from 0 to plus infinity. This line here is 1 minus t over tau. You can see that it's a linear function here. When t is equal to 0, its value is 1. And when t is equal to tau, its value is equal to 0. So I have here 1 minus t over tau. And then this changes. It's not to plus infinity. It's only up to tau, because after tau the function is equal to 0. And then I have cosine omega tau d omega t dt. Now, this splits into two integrals. One is integral t goes from 0 to tau cosine omega t dt. That one is easy to evaluate. And the other one is also table integral when t goes from 0 to plus tau, 1 over tau t cosine omega t dt. Now in appendix
2 is missing.
there's 2 here, right, in front of, because I'm integrating only over the positive t. Now the first one, it's an easy integral of the cosine is a sine, so this becomes 2 sine omega t when t goes from 0 to tau. The second one is a table integral here, which is given as 1 over tau, and then if we go to page 50 of your book, you have here omega squared. Then we have cosine omega t, and then plus omega t sine omega t evaluated from 0 to tau. Right? So this
First part. Divided by omega in the first part.
divided by omega here. So this is 2 times sine omega tau over omega minus, and then here I can write this as 1 over tau omega squared. When I substitute tau to the first term, I have cosine omega tau minus 1 plus, when I substitute tau for the second term, this is sine omega tau. And then you can see that some of these terms will cancel out. I have 2 times, then sine omega tau over omega, and then you can see this tau and tau cancels, and this becomes minus sine omega tau over omega, so that cancels. So the only term that is left is this middle term here, which is 1 minus cosine omega tau over tau omega squared. Now, what we can use is this trig identity. 1 minus cosine alpha is 2 times sine squared of alpha over 2. So this becomes 2 times sine squared omega tau over 2. And then here I can write omega tau over 2 quantity squared. And let's see what I have to have here to make everything balance. Omega squared, then I have tau squared, and I used to have single tau, so I have to divide by tau. And I'm dividing by 4, so I have to multiply here by 4. So this becomes 1/2 sine squared omega tau over 2 over, and then there's a tau here, omega tau over 2 squared. And this is 1/2 sinc omega tau over 2. So that's, and there's a tau missing here, tau over 2 sinc omega tau over 2. I see this is different than what's in the table. No, it's the same, except that they have omega tau over 4. Why would they have over 4? I think it cannot be over 4. Unless this tau here is power 2. Okay, so that's sinc squared here. So that's the Fourier transform of the lambda pulse. That's of the duration of lambda of 2 lambda, right? This duration 2 tau. Okay, so going back to the problem, this was a problem 7.3.3.1. So this was problem 7.3.2. So it says, use this information that we have here to determine the Fourier transform of some of these pulses that are given in this figure here. Well, if you look at, for example, pulse, let's say this would be x3 of t, that looks somewhat like this. The key here is to represent these signals as a known combination of known functions. So this would be x3 of t, and this is minus 2, and this is plus 2. So if you look at this function here, x3 of t can be written as rectangular pulse centered at the origin with a width of 4. That would be this square pulse here. And I would have to multiply this guy by 2 to get the proper magnitude in the middle. So it's a rectangular pulse of the duration 4 and the magnitude of 2. And then I can say this is minus this lambda pulse that has a magnitude of 1, that centered the origin as well, and then the tau in this case is 2. Right. So that's the x3 of t. And then Fourier transform, now x3 of f, or rather omega. We determined the Fourier transform of the rectangular pulse just earlier today, and we saw that the rectangular over t over tau is going to be 2 times tau, which in our case is 4, and then sinc omega times tau, which is 4, divided by 2. So that's the Fourier transform of the first part, and then minus, based on our derivations here, this is minus 1 times the Fourier transform of this one. This is a pulse of the triangular pulse for which tau is equal to 2. So this becomes 1 times 2 over 2 sinc squared omega times 2 divided by 2. Okay? And that can easily be written. Let me use this section of the board here. So it's 8 times sinc of 2 omega minus sinc squared of omega itself. And so that's how you would do all of these problems. The trick is to express the functions that are given here as a combination of triangular pulses and square pulses. Let me just do another one. Let's look at x5 of t. x5 of t looks like this. It starts minus 1.5, minus 0.5, 0.5, 1.5 t. And then this is 1 in this area. And then it kind of levels down here. So this is x5 of t. Well, how do I represent this one? Well, I can see that this x5 of t consists of 2 triangles. One is going like, let's see, let's try. I can say that this is see how would I put this together. Let's say I have first triangle that looks like this, second triangle that looks like this, right? So that gives me this section here, correct, and this section here, correct, and then I need to add this triangle that exists in this area. So I would say x5 of t is going to be, this is lambda of t plus 0.5, where tau is 0.5, plus lambda of t minus 0.5 divided by 0.5, and then plus I need to add this section here. So this would be what would be the easiest way to add this? Well, I have to add here 0, and I have to add this guy, right? Yeah. So this will be plus lambda of t over 0.5, if I'm not mistaken. So you have this triangle plus this triangle to take care of this, and then in the middle you have this triangle as well. So there are 3 triangles that added together would give you this waveform here. And this is very easy to evaluate. The Fourier transform of this triangle is given here. The tau in this case is equal to 0.5. So it's, let me just do this one here first. So this is 0. So it's 1/2 divided by 2 sinc squared of omega times 1/2 divided by 2. And then I have 1 for this guy. I have plus e to the j omega times 0 or over 2 for this one, and plus e to the minus j omega over 2 for this one, right? I have 3 triangles. This is the Fourier transform for the one that is in the middle. This is the Fourier transform, the one that is shifted to the left, and this is the Fourier transform for the one that's shifted to the right.
Divided by 2, not by omega. Sinc squared omega.
Sinc squared omega times tau divided by 2. 2, not omega. 2. Correct. Correct. So that's how you would use these kind of properties in the problem. Let's do this one more problem. Let's see, 7, 3, 4. Seven, 3-4. We have the Fourier transform. Okay. Use the time shifting property to show that if x of t has a Fourier transform x of omega, what is the Fourier transform of x of t plus capital T plus x of t minus capital T as a Fourier transform? Well, this one is very easy. If we already know that if x of t has a Fourier transform x of omega, then x of t plus minus any tau, or capital T, has a Fourier transform x of omega e to the plus minus j omega capital T, right? This is called shifting property of the Fourier transform. If we shift in a time domain, we're just phase delaying or advancing in a frequency domain. So if I now apply the Fourier transform of x of t plus capital T plus x of t minus capital T, this is x of omega e to the j omega t plus x of omega e to the minus j omega capital T. If I pull x of omega as a common, this becomes cosine omega t minus, sorry, I'm kind of going ahead of myself. So it's e to the j omega t plus e to the minus j omega t, and then I'm going to divide by 2 and multiply everything by 2. You recognize that the term in a square bracket is cosine, so this becomes 2 times x of omega cosine omega capital T. So this question mark here is the cosine 2 2x of omega times cosine omega capital T. So that's 734. Let me get another 739 is an interesting problem overall. So let me go through that one because it has a very distinct physical interpretation. So this is 739. It says that if x of t has a Fourier transform x of omega, and if the bandwidth of x of t is b, show that x to the nth power of t has a bandwidth n times b. Okay? First, the notion of the bandwidth. We say, if you look at the Fourier transform of signal x of omega, for a lot of signals, it is possible to define some value b for which x of omega is identically equal to 0 when omega is greater than b. In other words, the signal does not have the components outside of this b. B is called the bandwidth. And a signal that has this property for which there are no spectral components outside of some range from 0 to b is called band-limited signal. And that's one of the fundamental properties that we seek in a signal, to be band-limited for various purposes. One of the most important one being that we can show that if the signal is band limited, that you can successfully sample the signal and then recover it from its samples. So if my x of t is limited to the bandwidth from 0 to b, then what is the bandwidth of the nth power of xn of t? Well, the easiest way to do that is to kind of look at what happens first when n is equal to 2, n is equal to 3, and so on, and then deduce what happens to when n is any power through the method of induction. So let's first look at what happens is when n is equal to 2. Then we are looking at a Fourier transform of x of t squared, which I can say that this is Fourier transform of x of t times x of t. Now, Fourier transform of the product of the two functions is the convolution of their Fourier transforms. So this is equal to 1 over 2 pi, or let me just do it just notationally, x of omega convolved with x of omega. So to get the Fourier transform of the product, I have to convolve the Fourier transform. Well, what do we know about the convolution? Well, if the duration of this signal here is b, or rather 2b, right, because it's double-sided here, then, and the duration of this signal in the frequency domain is 2b, then the duration of the convolution is the sum of those two. So if how do I write that? If x of omega is different than 0 for omega smaller than b, then x of omega convolved with x of omega is different than 0 for omega smaller than 2b. Why? Because if I take the convolution that has the duration of 2b and I convolve it with itself, I'm going to get a signal that has twice the, so to speak, duration in a frequency domain. So let me call this signal x2. Let me call the signal x of t times x of t. Let me call this signal, define this to be x2 of t. And we saw that the bandwidth of x2 of t is going to be equal to 2b. Now let's take a look at n equal 3. We're now looking for a Fourier transform of x cubed of t, which I can see as a Fourier transform of x of t times x squared of t, which is a Fourier transform of x of t times x2 of t. Right? x2 of t being the signal, x squared of t, for which I already determined the bandwidth of the Fourier transform in the frequency domain. So this becomes now x of omega convolved with x of 2 of omega, where x2 of omega, is the Fourier transform of x squared of t, x2 of t. Now, what is the bandwidth of this one? It's b. What is the bandwidth of this one? 2b. Therefore, the bandwidth of the whole thing is 3b. And so on. So if I know, if I assume now that the bandwidth of x to the n of t is n times b, what is the bandwidth of x n plus 1 of t? So Fourier transform of x n plus 1 of t is going to be equal to the Fourier transform of x of t times x n of t, which is equal to x of omega convolved with x n of omega. And this one has a bandwidth of b, this one has a bandwidth of n times b, therefore the total bandwidth is n plus 1 times b. So we demonstrated that for n equal 2, the bandwidth is 2b, and then if we assume that for n x to the n of t, the bandwidth is n times b, then we get that for the next one, it is, for n plus 1, is n plus 1 times b. That's proper induction mathematically that shows that the bandwidth, whenever you raise a signal to the nth power, the bandwidth actually goes and linearly with the power that you raise the signal to. So x to the 3 of t will have 3 times b, x to the 4 times b, and so on. Now this is a formal mathematical proof, right? That's satisfactory as far as this problem is concerned. But let's take a look at, let's give it a little bit more of insight, kind of, because this property is very useful, and it comes quite often when we're dealing with the signal in communication. So let me give it not as precise proof, but probably more intuitive proof than this one. And to do that, what I'm going to look at is a special signal. Let me call this x0 of t, that consists of two frequency components. Let's say a cosine omega 1t plus b cosine omega 2t. So how does this signal look? Well, I'm just going to draw it for a positive omega. There are two sinusoidals. One is at omega 1 and the other one is at omega 2. what is the bandwidth of the signal is equal to omega 2, right? Because you're not extending past omega 2. So let's take a look at x0 squared of t. What does this one look like? Well, this is a cosine omega 1t plus b cosine omega 2t. And this is going to be squared. So this is going to be a squared cosine squared omega 1t plus b squared cosine squared omega 2t, and then plus 2ab cosine omega 1t cosine omega 2t. So this is now equal a squared. This cosine can be written as 1 plus cosine 2 omega 1t divided by 2, and plus b squared 1 plus cosine 2 omega 2t divided by 2, and then plus ab cosine omega 1 plus omega 2t, and then plus cosine omega 1 minus omega 2t. Right. So what's the moral of the story? If you take the signal that has two cosines, what happens, you end up with 4 frequency components, actually 5. One is at DC, this is this a squared over 2 plus b squared over 2. Then you have the twice of this guy, twice of this guy, and then the sum of these two, and then the differences of these two. So the bandwidth of x0 squared of t is equal to 2b. But why is it 2b? Because when you square this frequency, that is highest frequency in the spectrum, that one gives you the component that is twice, right? So that's the reason why. Now, if you look at now what happens if I now look at my signal here, and if you have a signal that looks like this, then in a frequency domain, this is x of omega, you can think of it as consisting of many sinusoids, right? Each one of them being, contributing small amount to spectrum, but they're all kind of adjacent to each other. If I square this signal, what will happen? For every spectral component here, I'm going to get a DC contribution, and I'm going to get twice the frequency, right? And so this, for example, this one here will give me twice, and then DC, right? So if this is some omega 0, then I'm going to get 2 omega 0 and a DC component. The one that will give me the highest component is this guy here. So let's call this omega max. When I square it, I'm going to get DC component also, but I'm going to get the component that's at 2 omega max. Right? Now, I'm going to get also the cross terms. The cross terms are going to be the additions and differences of the pairs of the spectral components. But you can see right away that if I pick 2 spectral components here, the sum will never exceed this 2 times omega max. And the difference is, also never be outside of this range. So all the other pairs of the spectral components that I pick will give me the spectrum in this range. So the range of the components that is occupied by the square of a signal will be between 0 and 2 omega max, where omega max is the maximum frequency in the spectrum of the signal. doing the same kind of analysis, you can demonstrate that, if you cube, a whole bunch of sinusoidals, then you're going to extend all the way to 3 omega max and 4 omega max and so on. So that's more, I would say, intuitive thinking of what is happening here. If we limit it to just squaring, you can see that when you square all of these sinusoidals that you have here, you get essentially 3 kinds of components. You get components that are piling at DC, then you get components that are twice the frequency of each spectral component here, and then you get the components that are sums and differences of all of these spectral components here. Out of all of these 3 terms, the one that is giving the highest frequency in the spectral domain is going to be twice the frequency of the maximum here. And that one is the one that determines the bandwidth of the signal. Okay. So these are some of the problems associated with the lecture 16. We'll continue, I guess, on Tuesday again.